thought I'd put it on. Sorry, thank you very much.
Now it's
Yeah.
recording.
It's recording, no? Thank you.
Yes, ma'am.
Yeah, it wasn't. So I thought I had put it on. So thank you very much for pointing it out. So let me just take this step and explain this to you. Okay. All right. So I'll just
Okay, ma'am.
take this step. Okay. So let me go to the new page. All right. So what was written over there? Summation over M. Okay. U. Let me just
Yep.
get the same thing.
UM.
U M N. Right. Yeah. U M N
Yes.
delta J M. Okay. U M N delta J. What was it? I keep forgetting.
Delta JM, ma'am.
Yeah, delta JM. Okay. So now let us just here 1 second. I have to admit somebody. All right. Let us give this numbers. Okay. So let M go from 1 to 4. Let us say. Okay. Automatically your N. Let us give it a fixed value. N is a fixed value, right? Just 1 second. Need to admit some more people. All right. All right. Just 1 second. Did I not admit somebody? I just 1 second. Yeah, there are more people. All right. So let n be some 3. Okay. Yeah. And let j be some 2. Okay. Let us assume. Yeah. Now let us see how it works out. Okay. So we have now, I will write this down specifically. Okay. The same expression with these values. I will write it out. M going from 1 to 4. Okay. U, M. And what is N now? N is 3. Delta. And what is J? J is 2. And then what is M again? M, I mean, it's just M, right? Okay. So now let's write it out. Okay. So this will be then U1, 3, because M will be 1 first. Delta 2, 1 plus U1. Now M becomes 2. Okay. So U2, 3 delta 2, 2 plus U 3, 3 delta 2, 3 plus U 4, 3 delta 2, 4. Okay. So please note M is 1 here, M is 2 here, M is 3 here, and M is 4 here. Okay. So I've written down all the terms. Are you with me so far? Have you gotten this?
Yes, ma'am.
Okay. Now, what is delta 2, 1, please? Tejashri, what is
Yes,
delta
ma'am.
2, 1?
Delta 2 is 0.
Yeah.
J is
So,
not equal to
U1, 3, it will be into 0, right? Plus
yes, ma'am.
U2, 3, what is delta 2, 2?
1.
1.
1, 1.
Yeah, correct. U3, 3, delta 2, 3?
0.
0. U4, 3, delta 2, 4?
0, ma'am.
Perfect. So now what will I get? First term is 0. Second term I'll get U2, 3. Plus third term I'll get 0. Fourth term I'll get 0. So what is this
Yes,
now?
ma'am.
I get U2,
2,
3.
3.
Correct? So which is nothing but, let's now replace this with N and this with J. Okay. So what have I got here now? I have got
J,
nothing but U, J,
J,
N.
N.
Is this clear now? How this
Yes, ma'am.
happens? Yeah. So let's
Yes,
go
ma'am.
back. Is that what we got over here? U,
Yes, ma'am.
J, N.
Same.
Yeah.
Yes,
Is
ma'am.
this clear? Okay, good.
Yes, ma'am.
Anybody else? Any other doubts? Any other doubts, please? Okay. So we have proved that this is unitary. Okay. Let's take it a further step from there. All right. Is that all right now? Okay. So I've
Okay,
proved that
ma'am.
this is unitary. Now we'll move further. Okay. Let's, oh, what happened to this? I'm going to go to the next page anyway. So now let us imagine you have some psi. Please note this is different from the small size I was writing. Okay, I was writing these small size. This is different. Okay, these are eigenfunctions. Okay, in representation 1. This is the basis set in representation 1. This one. This is some psi belonging to the vector space. All right. So this is some psi belonging to the vector space. So we should be able to write this psi as equal to summation over I, okay, some Ci, these psi i's, okay. So please remember these are the eigenfunctions. Remember this, that these are the eigenfunctions, or rather let me make it more specific, complete set of eigenfunctions in representation 1, correct? Representation 1. All right. So we should be able to write psi like this. How do we know that we should be able to write this guy like this? Because these psi's are a complete set, right? Because if they are complete, then any wave function that you pick up, you should be able to write it as a linear combination of these functions, correct? Similarly, I can write this psi as equal to summation over I C prime I phi I. Okay, why? Because, one second, somebody else has come in, let me admit. Because the phi I also forms a complete set. We know this. How did we write it down? With the closure relation, right? We did summation over I phi I is equal to identity. Okay, so we know that this statement is also true. So the question I'm asking now is, what is the relation between Ci prime and Ci, or rather Ci primes and Ci's, okay, because there'll be more than one. Okay, so what is the relation? This is what I'm asking. Okay, so now please remember, how do I write down the Ci prime? This is going to be nothing but inner product of phi I with this psi. Okay, all right, so this is how I will define a Ci prime. Please note, we have been talking about this all along, so hopefully if you go back a few pages of your notes, you will see this. Okay, yeah, this is how the coefficients Ci primes are defined. Okay, or any coefficient is defined. Okay, so it's an inner product between the phi I and the wave function itself. All right, now let's write this out. So now I'm going to basically write this psi as this linear combination. Okay, so I will take, say, some summation of m, and then I will write this phi I. Okay, I don't want to use the same I again. All right, and then I will write it. Okay, I'm actually not doing that. I'm doing something else. I'm using the closure relation of these psi i's. Okay, so I will write it as psi m. Okay, so I have introduced this over here. Okay, and this. How did I do that? Please remember, these, the psi i's are a complete set, which implies that I can definitely write this closure relation, right? Here I'm just replacing this I is anyway a dummy. I'm replacing it with m and I'm putting it here. Is there any doubt? Has everybody understood what I'm doing over here? What happened? Is this clear? I'm using the
Yes, ma'am.
closure relation for the psi i's. Okay. So now
Yes, ma'am.
let's see what happens. I will get over here m phi I psi m. What is this going to be? This is going to be nothing but Cm. Okay, because please remember, just like over here, this was Ci prime because you did phi I with psi, sorry. Similarly, this is going to be nothing but Cm. All right. Now, what about this? If you remember our definition, let me go back. Somebody is waiting to be admitted. Let me go back. Okay, look at this definition over here. Yes, of UJN. So let's now go back. So, okay, so here this is going to be nothing but UIM. Okay, so summation over M, UIM CM. Okay, so now let's look at it. Your, okay, this is how you will write. So this is some CI, okay, which is equal to, this is your U matrix, correct? So this is going to fix the row number. Okay, so this will be U1, UI2, UI3, and so on and so forth, right? And here you have now your C1. So this is C prime, sorry, C1, C2, C3, like that. Okay, so this will multiply this, plus this will multiply this, plus this will multiply this. So this is essentially matrix multiplication. Did you get it? This into this. Okay, it's a matrix multiplication. So if I want to write it as a matrix, I can write it as C prime, okay, is equal to U C. Okay, where the C prime represents psi in the basis set of phi I. All right, and the C represents psi in the basis set of psi i's. Okay, is this clear? So this you can also write it as psi prime if need be. Okay, we have written it both as psi over here, but that is the way you understand. So this, please remember, is a matrix transformation from a one to the other. Is this clear? Has everybody understood this? Then we can move on to the next thing. Okay, so this is the relation between the Ci primes and the Ci's, that your Ci prime is equal to, okay, summation over M UIM CM. Okay, right. So now we have another thing to prove. So we have proved the relation between the coefficients and thereby also the wave functions. So we have proved that the wave function psi I prime is transforming as this, okay, from this relation. Okay, so we have proved this, right? So now what we need to prove is that the operators are transforming how? As A goes to UA U dagger, right? So that is what we need to prove now. So let's do that. So we need to prove. So how do I write it down? Okay, so how the transformation of operators. Okay, all right. So now what you have to remember, that if I can have an operator in the representation in the psi I basis, right? Basis. I hope everybody understands the meaning of basis. Okay, so like I dagger I, J, K, okay, the unit vectors I, J, K are the basis vectors for three-dimensional space in Cartesian coordinates. Similarly, R, theta, phi are the unit vectors or the basis set for three-dimensional space again in spherical polar coordinates. Okay, so you can have an A representation in psi, and then you know that your A, I, J, okay, the matrix element will be nothing but this, right? And please remember, this is your operator A, okay? All right, and this is Aij, it's representing A in psi I basis, okay? So now similarly, if you want to represent your A prime ij, what is this? This is nothing but A in the phi I basis, okay? So what will this be? This will be nothing but phi I operator A phi j, okay? So it is the same operator. Remember, it is the same operator. You are representing it once like this and in the phi i's like this, okay? I hope this is clear. So now let us, what do we have to prove? We have to prove that A prime is nothing but U A U dagger. All right. So let us start off. So we have to thereby prove that A prime, say Mn, is nothing but U A U dagger Mn. All right. This is what we have to prove. So let's start off with the left hand side. Okay, just 1 second. Somebody needs to be admitted. Let's start off with the left hand side. And we have now over here A prime Mn, which is going to be what? It is going to be nothing but phi m operator A phi n. Yeah, I hope everybody agrees with me. I've basically taken it from this step. Okay. Now let's do one thing. Let us introduce using the closure relation two summations now. Okay. 1 over k, 1 over L, and then we will write it as phi m, okay, and then I will put a psi k a, okay, then I'll put a psi l phi n, okay. So please note, I have introduced two closure relations. What are those two closure relations? One is summation over k psi k is equal to I, and the other is summation over L psi L is equal to I. It's the same thing, but I'm just using different indices. Okay, so one has come here along with this, and the other has come here along with this. Okay, I hope it is clear to everybody. Now, so therefore, your A prime Mn is going to be equal to, let us write again, summation over K, summation over L. What is phi m psi k? Phi m psi k is nothing but U m k. Okay, so I'll just go back. We have defined it here, not here, here. No, not even here. Here. Okay, you see this definition? We have this, okay? And this definition I'm basically using here. Okay, UMK is nothing but inner product of phi m with psi k. Then what do I have over here? I have this element here. What is this going to be? Using this definition here on the top of the page, I will write it as A K L. Okay. And then we have over here, this is going to be nothing but phi n psi L. Sorry, I don't mean to write it like that. Star. Okay. Yeah, phi n psi L star. Again, now let us write it down. Summation over K, summation over L U M K A K L, and this is going to be nothing but U N L, right? U N L, and we'll have a star over here. Okay, U N L star. So now what do we have? Yeah, so UNL star. So we can write this now as summation over K, summation over L, U M K A K L, and this now is nothing but U L N dagger. Okay, if you take the transpose conjugate of U, if you take the lnth element, it is going to be nothing but this. Okay, this one here. All right. So now thereby, if I want to write it fully, I can write it as U A U dagger. I have essentially the mnth element. Okay, so hence proved. Is this clear to everybody? How I ended up proving this relation here? Is it clear what I did? So essentially, please remember, I started off with this, and then I introduced two closure relations here and here, and the rest just follows from the definitions. Is this all right? Has everybody understood?
Last step, ma'am.
Yeah, tell me. Which last step?
ಇದು ಲಾಸ್ಟ್ ಸಮೇಷನ್ ಆಫ್ ಕೆ ಅಂಡ್ ಸಮೇಷನ್ ಆಫ್ ಎಲ್ ಯು ಎಂ ಕೆ ಎ ಕೆ ಎಲ್ ಲಾಸ್ಟ್ ಸ್ಟೆಪ್ ಯು ಡ್ಯಾಗರ್ ಅದು ಯಾವ ತರ ಬಂತು?
ಅದೇ. So this is the thing, right? If you want to get u dagger ij, how will you write this? What is the relation with the element in the unitary matrix itself? This is with the transpose conjugate, right? Allah? Yeah, this dagger.
Yes, ma'am.
It means that it is transposed and conjugated. This you will write it as A J I star. Isn't it?
Yes, ma'am.
So same. I have used just that relation here.
Okay, ma'am.
Got it?
Yes, ma'am.
Okay, good. Any other doubts?
Excuse me, ma'am.
Yeah, tell me, Tejaswi.
Ma'am, next step. UA, U dagger of MN you wrote, no, ma'am?
Yeah.
That step you explain in
Yeah,
once
because
again,
see,
ma'am.
you're multiplying, right? You're
Yes, ma'am.
multiplying. So these are all dummy indices. This KK
yes,
is repeated, it will go away. This LL is repeated, it will go away. Correct? So you
Okay,
will
ma'am.
get U A U dagger. So you
MN.
get U A U dagger M N.
N. Yes, ma'am.
From matrix multiplication, that will come out.
Yes, ma'am.
Okay, is that all right? Is this clear?
Yes, ma'am.
Okay. Any other doubts, please? Anybody has not been able to follow the math, please tell me, I will explain. Okay, so now we will go to quite an important theorem, all right? And the last theorem with unitary transformations. After that, we will move on to something quite interesting, which is that we will actually use matrix methods to solve, okay, some of our problem. Okay, so let me just tell you the last bit of it. I have papers scattered all around. I can't find what I need. Okay, and please remember now, yeah, what did we tell once upon a time? That if you have a Hermitian matrix, then it can be diagonalized using a unitary transformation, right? Long back we had talked about this, that a Hermitian matrix can be diagonalized using a unitary transformation. This was a fundamental theorem of matrix mechanics. So let me write it down again. It's a fundamental theorem of matrices. And what is that? A Hermitian matrix can be diagonalized. What do you mean by diagonalized? That you can make it a diagonal matrix. Okay, it can be diagonalized using unitary transformations. Okay, yes. Now, what did I say at that point of time? If you remember, I had said that the unitary transformation doesn't change the physics of the situation, correct? And I hope by now you're all convinced, okay, that unitary transformation doesn't alter the physics. So I'm reminding you now that Hermitian matrices can be always diagonalized using a unitary transformation. So without changing the physics, you can diagonalize a Hermitian matrix. So if there is an A, okay, it is in a non-diagonal form. Okay, it's in a non-diagonal form. Then what can you do? You can use a unitary transformation. What is the advantage of the unitary transformation? Physics does not change, right? Correct? Everything remains the same. Yeah, it does not change, right? And then you can come to a diagonal form. Everybody with me right now? That you can take any operator, even if it is in a non-diagonal form, you can do a unitary transformation to make it a diagonal form. How do I know? Because of this fundamental theorem of matrices. Okay. Now, in the diagonal form, we learned something interesting, right? What happens in the diagonal form? Today itself, we learned that the trace of A is what? Sum of its eigenvalues. Right? I hope you remember this, that it is the sum of its eigenvalues. Is there any doubt so far now? Anybody has any problems with what I have stated right now? If you do, please ask me. I'm connecting with things which I also told you long back. Is this clear? Somebody tell me something. Otherwise, I think you've
Yes,
all
ma'am.
gone away.
Yes, ma'am.
Yes,
Huh? It's
ma'am.
okay, right? Good. So now I'm going to tell you something pretty interesting, and that is this, that the trace of a Hermitian matrix is unchanged under unitary transformations. You may have learned this as a theorem in matrices, in matrices, yeah. But right now we are going to cast it in the light of quantum mechanics. Okay. So what am I saying now? Whether now the Hermitian matrix is in the non-diagonal form or the diagonal form, the trace remains the same. What is trace once again? It is the sum of its diagonal elements. Okay. So the sum of the diagonal elements remains the same whether it's in non-diagonal form or in diagonal form. But we know that in the diagonal form, it is the sum of the eigenvalues. Yeah, we know it is the sum of the eigenvalues. So please remember, a Hermitian matrix, no matter what form it is in, whether a diagonal, whether non-diagonal, the sum of its leading diagonal elements, which is its trace, remains unchanged, and it is always the sum of its eigenvalues. Okay, so we will prove it now. Okay, so we will prove it. So we will prove this now. So how do we prove it? Let us imagine that you have an operator A which has gone to an operator A prime, which is nothing but U dagger. And what we have to prove is that trace of A prime is same as trace of A. Okay, this we have to prove. All right, so how do we prove this? So let's take trace of A prime. What is trace of A prime? It is summation over, let us say M, A prime MM. So essentially we are summing over all the elements, okay, where the row number is equal to the column number, and that will be only true in the leading diagonal, right? Row number will be equal to column number. So we are summing only those elements, okay? So A1, A prime 1 1 plus A prime 2 2 plus A prime 3 3, like that, okay? So now let us, but we know what A prime is. A prime is nothing but this, correct? So we'll write down over here summation over M U A U dagger M M. Okay. Now let's open it up. So this is summation over M. Okay, so I'm going to use the same logic that I used earlier for multiplication of three matrices, and I'm going to introduce a K and I'm going to introduce an L. So here what we will have, we'll have U M K A K L U dagger L, sorry, K, yeah, L N M, sorry, yeah, it is M and M, right? Yeah, L M. All right, so this I've just used. For some reason I was looking for an N and not an M, that's why I got a bit confused, but it's MM, right? It's MM over here. Okay, so this is how I'm writing it down. Now let's go further. So now please remember, these are just numbers, right? They are elements of a matrix. They are just numbers, and numbers always commute. Okay, so I'm going to write it over here. UMK AKL U dagger LM. These are just numbers, right? And numbers, you can rearrange it any which way you like because numbers commute, right? So now I'm going to write this as summation over M, summation over K, sorry, K, summation over L. I'm going to write it as UMK U dagger LM AKL. Right? In fact, I'm going to change it a little. I'm going to pull this K out. I'm going to pull this L summation out. I'm going to write this M, and then I'm going to write U dagger LM UMK AKL. Okay. Now what do we know? We know that U dagger U is equal to I. Yeah, which means that U dagger, what is this actually? What is this element? Can anybody tell me? This is nothing but U dagger U element LK. Yeah?
Yes, ma'am.
So this will be U dagger U LK is going to be nothing but delta LK.
LK.
So thereby we have now over here, I hope I'm going to be able to write it here itself, summation over K, summation over L, delta L K A K L. Okay, I think it didn't come out properly. So I'll write it in the next page. I'm sorry. Okay, I'll write it in the next page. So what did we have over here? So we had trace of A prime is going to be equal to, I'm going to write the last but one line, okay? So summation over K, summation over L, okay? And then I had written in brackets summation over M, U dagger, what was it? L M U M K, and then I had A K L. And we concluded that this should be nothing but delta L K. So we have now over here summation over K, summation over L, delta L K, A K L. So obviously, since that delta Lk is there, only when L is equal to K, it will survive. And please note there are two summations here. So only one summation will stay. You can either write it as summation over K or summation over M. Doesn't matter. Summation over L, it doesn't matter. K has to be equal to L. Okay. So we can write it as a single summation over K, A, and L has to be equal to K. So we'll get AKK. What is this now? This is a summation of those elements of A where row number is equal to column number. So obviously this is nothing but the trace of A. So therefore trace of A is constant, or we can say unaltered, okay, under unitary transformation. All right, yeah. Just 1 second, somebody is waiting. Okay, it's unaltered under unitary transformation. Also we know that what else do we add to this? We can add to this that a Hermitian matrix can be diagonalized using unitary transformation, right? Which I told you before means that you can go from a non-diagonal form to a diagonal form, right? And in the diagonal form, trace is equal to sum of eigenvalues, and thereby taking, and now we know trace is unchanged under unitary transformations. And what does this, all these arguments imply? It implies that trace of a Hermitian matrix is equal to sum of eigenvalues. It does not matter whether it is in diagonal form or non-diagonal form, it is always the sum of the eigenvalues. Is this clear to everybody? Has everybody understood? Yes? Yes or no?
Yes, ma'am.
Okay, I'm going to stop the share right now. And we are going to start off on a new topic now. And this is that we are going to look at the matrix method of trying to solve the, okay, this is not a paper I really require. Matrix method of trying to solve the simple harmonic oscillator. All right. So now all of you have, done harmonic oscillator. Yeah. You're doing it in classical mechanics again. Can somebody tell me what is a simple harmonic oscillator? How do you define it? Because classically, tell me classically, the quantum mechanics version we'll worry about now. Okay. So how do you define a simple harmonic oscillator? All of you know this. You can give me your BSc definition, PU definition, doesn't matter. Just tell me. What happened? Everybody's forgotten or what?
Ma'am, to and fro motion of a particle.
To and fro motion of a particle. Okay. So anybody else? Anybody has any other definition? See, to and fro motion of
Force
a
is
particle would
proportional
make
to-
it an oscillator, right? That's perfectly all right. So you've got the oscillation part correct. What makes it a
in the
harmonic oscillator?
oscillatory-
Yes. Who's answering, please?
Sumant, ma'am.
Yeah, tell me, Sumant.
Ma'am, oscillatory motion under the recording force proportional to the amount of displacement in the equilibrium position, ma'am.
That's correct. That's correct. Yeah. So you have essentially, so let's ask ourselves, why should something go to and fro? Like who answered the first question? Supriya, right? Supriya told us that it's a back and forth motion. It's a to and fro motion, which means that it goes somewhere, it stops, it comes back, right? That's what we mean by oscillation. So now we are asking the question is, why is it coming back? Okay. So obviously now Sumant has brought in the second point. That is that it is getting a force which is restoring it. What does restoring mean? It is putting it back in the original condition. Okay. So what is happening now? That force, there is a force acting on the particle and it is trying to get it back to the first position. What is that first position that we are talking about? Or that mean position? Something which we call as an equilibrium position, right? So now Suman told us that harmonic oscillator, this restoring force is a little special. Okay. Every oscillation will definitely have a restoring force. It means that if it is the moment it is coming back to the original position, means something is bringing it back. It's not going away. It's not running away. Something is bringing it back. But then in the harmonic oscillator, that force is a bit special. The force increases in magnitude. Okay. As you move away from the equilibrium position, and it's directly proportional to that displacement. Okay. So if you have an equilibrium position and you have the particle which is moving away, the more it moves away, that force becomes stronger and stronger. But what is the direction of the force? Force is a vector, right? So can somebody tell me what is the direction of that force, the restoring force? Magnitude, you told me, it is proportional to the displacement. Correct. What about the direction? Which way is the force pointing?
Towards rest, ma'am.
Towards the rest. We won't call it rest because it doesn't come to rest, but you're correct. It is towards the equilibrium position. Absolutely correct. Okay. Thank you, Amrita. So now, okay, let us try and let me just go and share my iScribe once again. Okay. So we will go to a new page now since we are starting on a new topic. So essentially the situation is like this. You have an equilibrium position. Okay. And you have a restoring force. So I'm going to call it FR, which is always pointing towards the equilibrium position. And it is equal to some
iScribe is not visible.
Sorry? Screen is not shared, is it?
iScribe is not visible. No, ma'am.
Okay, 1 second. I'm sorry about this. Yeah, you're right. For some reason, I think I have done something silly over here. Okay, I didn't share it through the... Yeah, okay. Can you see what I've written? Is it visible? Is what
Yes,
I've
ma'am.
written visible? Okay. All right.
Yes, ma'am.
So what I'm saying is that this is your equilibrium position. This is your restoring force, which is always pointing towards the equilibrium position. And this is equal to K, which is a proportionality constant. We also call it a spring constant. Okay, and this is your displacement from the equilibrium position. Okay, so it is a minus, and this is also your vectorial thing. All right, so it is minus kx, minus meaning whichever direction the displacement, and this is pointing in the opposite direction. Okay, so this is what we have for a simple harmonic oscillator. Now, how shall we go ahead? Let us now imagine the whole thing in quantum mechanics. Okay, yeah, so let's imagine it, the whole thing in quantum mechanics. And we know that we have to write down this thing called the Hamiltonian. What is the Hamiltonian? I've told you it is nothing but the total
Kinetic energy and potential energy.
operator. Exactly, as I think it's Sumant who told me that it is
Yes,
nothing
ma'am.
but
Sumant, ma'am.
kinetic energy plus potential energy. Thank you. Yeah, just 1 second. Somebody has come in. So now kinetic energy is what? It is nothing but, how do you write it? Kinetic energy.
P square by 2m.
Can somebody tell me what is the formula for kinetic energy?
Half mv square.
Half mv square. Okay, so it's half mv square, but we are going to write it a little differently over here. We are going to write it as mv whole square by 2m,
2m.
which is equal to, what is mv? Momentum, right?
Momentum, ma'am.
Yeah, so I'll write it as p, so it's p square by 2m. Okay, so I'm going to write the kinetic energy as p square by 2m. What about your potential energy? Can somebody tell me what is the potential energy of a harmonic oscillator?
Half kx
Half
square.
kx
Minus
square.
K.
Wonderful.
Half K.
Half kx square. You know, I'm very, very proud of all of you. This is the first class which has given me the perfect answer. Everybody else tells me it is MGH. Okay. So I'm very, 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 very happy with you. Okay. Yeah. So half kx square. Absolutely correct. So now let us write down the Hamiltonian again. It is nothing but p square by 2m plus half k x square. Okay, now we are going to write it a little differently. All right, we will not really use this k. Okay, if you remember your can anybody tell me what is the time period of a harmonic oscillator? Does anybody remember?
Square root of L.
Yeah, square root of
2 pi root L by G.
2.
sorry. Okay, let's forget it. Let's write a proportionality. Okay, let's forget about the 2 pi and all. Okay, so what is this? Root of
Square root of L by G, ma'am.
L by G. You're getting into this thing, your simple harmonic, your pendulum again, right? Where is L over here? Where is G, right? So yeah, your answer is correct, but that is for a pendulum. All right. So it is actually m by
Of
k.
mk, ma'am.
M by k.
mk. M by k.
So
Okay.
you know that there is a, so this is actually, I think it will be 1 by 2 pi or 2 pi. It will be equal to 2 pi. Okay, this is basically what it is for a harmonic oscillator. So now if you want to write down for omega, okay, or this is, you want to get the frequency. What is your frequency? Your frequency is nothing but 1 by 2 pi root of k by m. Yeah, right? The way to
Yes.
remember is that k increases, restoring force increases, frequency will increase. M, on the other hand, will make the whole thing more sluggish. Okay, yeah, so it will be against a high frequency. Okay, it will be impeding, it's an inertial thing, right? So now what is 2 pi f? Can anybody tell me? This is nothing but angular frequency omega. Okay, so omega is equal to root of k by m. So let's take squares on both sides. We will get omega square and we will get k by m, which implies that k is nothing but m omega square. Okay, we are going to use this expression. We need that omega. Okay. So we are going to use that expression. So what we'll get over here now is p square by 2m plus half m omega square x square. Okay. So please remember the Hamiltonian of a simple harmonic oscillator is written as p square by 2m plus half m omega square x square. Okay. Everybody happy with this? You have understood each and every term? Yes?
Yes, ma'am.
Okay.
Yes, ma'am.
Good. So now let's look at it a little carefully. Okay. What do we have? We have a 1 by 2m over here. This is like a constant. Okay. It's like a number. And then we have an operator over here. Right? This is actually p square. Correct? The operator p, momentum. And it will be that to p in the x direction only, because we are talking about the linear harmonic oscillator. We are only worried about one dimension. Okay. And here you have again m omega square by 2, which is again a number. And then we have this operator square. Okay. So we are writing essentially, okay, this Hamiltonian in terms of one operator square plus another operator square. Okay. So now we are going to do something over here. Okay. So let me further refine it. The further refining will be that we will take out of this, since it's a harmonic oscillator, I'm going to justify this to you later. Okay. Right now you just go with me. I'm going to take out common a quantity which is h cross omega by 2. I'm going to take out this quantity. I'm writing it down on the page. H cross omega by 2. Okay, you will understand the significance of this later. So I'm going to take it out common. So this I'm going to write now. The Hamiltonian is equal to h cross omega by 2. And inside I'm going to get now p x square. Okay, this is an operator. I'm going to get essentially m h cross omega. All right. And then I will get over here plus, over here I'll get m omega by h cross x square. Okay. So this is the Hamiltonian for a simple harmonic oscillator as far as quantum mechanics is concerned. This is for a quantum mechanical linear one-dimensional harmonic oscillator. Okay. Now, as I said, you will see that this is essentially made out of two squares. Okay. So let us now discuss this separately. Okay. I'm going to discuss this separately. And let's see how we can write this. Okay. So I'm going to put this page away. I'm going to change the page over here because I don't want any confusion. Okay. So let us imagine, just forget about what we know so far. You had two quantities, c square and d square. Okay. You had c square plus d square. Can everybody see this? What I have written in this new page? C square plus d square. Yes?
Yes, ma'am.
Okay. How can I write this? I can write this as, say, c plus id into c minus id, right? I could have written it like this. If c and d were numbers. Just see whether what I have written is correct. Yeah, this will give us what? C square minus I CD. Then I'll have plus DC. And then I'll have a minus I square D square. Right? So this will give me, so I'll have to say the CD is the same as DC. And then what will I get? I will get C square plus D square. Because this I square is going to become minus 1. Correct? Everybody with me so far? Has everybody followed this step?
Yes, ma'am.
Okay. Now the assumption over here is that C D, and that DC were one and the same, correct? But now suppose I'm doing this with operators. Okay. So now I have some operator C square plus operator D square. Okay. So in that case, if I write C plus ID into C minus ID, what will I get? I will get C square plus I. First C will come and then D will come, right? So I should have written minus. Okay. So this is minus I C D. Then I'll get plus I D C. And then I will get plus D square. Right. Now if CD is not equal to DC, then this is also not equal to C square plus D square. Correct? So how do we get out of this? Okay, if I want to write this as a different expression, how do I get out of this? I can do it a little differently. I can say now, what about C minus ID into C plus ID? So here I will get C square plus I C D minus I D C, and then I have what? Plus D square. Let's put this guy here. This is C plus I D into C minus I D is equal to C square minus I C D plus I D C plus D square. Yeah. Now let's add these two. Okay, I'm going to add these two. If I add these two, what will I get? On this side, I will get C minus ID into C plus ID plus C plus ID into C minus ID is equal to 2C square plus 2D square. Okay? Or I can write C square plus D square is equal to half of C minus ID into C plus ID plus C plus ID into C minus ID. Okay? We can go further and write it as the C minus ID by root 2 into C plus ID by root 2 plus C plus ID by root 2 into C minus ID by root 2. Okay? Now we'll do one thing. We are going to call this guy some A plus and this guy some A minus. Okay? Then what will happen? This is going to be nothing but A plus A minus plus A minus A plus. Has everybody got this? I'm just saying that if you had a sum of two operators, squares of two operators, so a C square plus a D square, if C and D did not commute, then you would have to write c square plus d square like this, where a plus was this and a minus was this. Is this good? Has everybody understood what I'm trying to say?
Yes, ma'am.
Yes, ma'am.
Okay. So now let us look at what is the connection with the harmonic oscillator. Please look over here. You can see the harmonic oscillator is also a px square into some number into an x square. So now, given this, okay, so let's go back here. Our harmonic oscillator is nothing but, let me just get this thing correct, h cross omega by 2 into, we have over here a px square by m h cross omega, okay, plus m omega by h cross into x square. So our px square by m h cross omega is like our c square, right? Oh, 1 second, let me just be a little careful. Okay, so we'll have to be a little careful over here. All right, I think this is actually like d square. Yeah, and similarly our m omega by h cross x square is like our c square. Okay, so then we can define this a plus as equal to, actually we will write it more like a small a plus. I'm not going to be writing the, what do you call it, I'm not going to be writing it in capitals over here, and I'm not going to put the cap very often. All right, but this a plus, you should know, is like a new operator we are defining. And what is this going to be equal to? This is going to be equal to 1 by root 2. Please remember how we defined it as c minus id, right? So c is what? C is going to be m omega h cross to the power of half x minus, and then we have an I, and what is your D? Your D is going to be 1 upon m h cross omega to the power of half of px. Okay, this is how I'm defining a plus. All right, so I'll have to go to the next page, unfortunately, and define for you the a minus. So let me just do that. So similarly, okay, I'll have to change the page now, which is going to be a bit of a problem. Your a minus, which I also define as a minus, okay, is going to be, let me have a look at what I have written over here. It is going to be c plus id by root 2, right? So it is going to be nothing but c plus id by root 2. So it is going to be 1 by root 2. And how have I written my c? Let's go back again and have a look. C, if you remember, I wrote it as this, right? So it will be m omega by h cross. So it is going to be nothing but m omega by h cross power half x plus I, and then we'll have 1 upon m h cross omega is, I think, what I wrote, power half px. And this, as I told you, is essentially your a minus. Okay, so now how will you write your Hamiltonian? Your Hamiltonian will be nothing but h cross omega by 2 into, now what do you have over here? You have essentially your a plus a minus plus a minus a plus. Okay, so instead of writing it like, what had we written it earlier as? We had written it as p x's square by m h cross omega plus m omega by h cross into x square. Instead of writing it like that, we are now writing it like this. Okay? Is this clear? Is this clear? I'm going to
Yes, ma'am.
stop the share now, and I'm going to just talk to you for a few minutes and then we will stop. I realize that I've really gone through my time, right? No new share. How do I get out of this? Okay, so I will just stop share. Yeah, so I hope you've gotten it, and the idea, please remember, is to try and solve this in a very different way. We are going to use matrix mechanics to solve the problem of the one-dimensional oscillator. Meera madam is starting one-dimensional problems with you. She is going to do it by solving the Schrodinger equation. The Schrodinger equation, please note, is a differential equation. So you have to solve the differential equation to get your answers. But what we are going to do over here is that we are not going to solve the differential equation. We are just going to use matrices to do it. And you may have wondered, what is the idea of this A plus and A minus? Why is madam making, SB ma'am, making it more and more complicated? I am actually not making it complicated. And once you have finished solving it with Meera madam, you'll realize that this is actually the much more elegant method. It may look complicated at the beginning, but it is actually a much more elegant method of solving the same problem. And this A plus and A minus have special properties. You will realize that they have a property of changing the energy levels. Okay. So this is where we are going to come into quantum mechanics, where we do not have continuous energy levels, but rather we have energy levels. And these A plus and the A minus have the ability to help you either climb up or climb down in the energy levels. And that's why they go with the name something special, which is called as a ladder operator. Okay. With this, I will stop today. And I will meet you tomorrow at 4 to 5, right? I hope that you remember that class 5th May, 4 to 5, I have still booked you, all right? So see you tomorrow evening. Have a very nice rest of the day. So take care and bye for now. I'm going to stop the recording.